My name's Kevin Ferretti. And today I'm going to be giving an overview of mechanistic interpretability. And when I say overview, I mean overview. Like, this is very, very high-level introduction, not going to get too much into the technical details. And my goal is basically just to get people interested in it, and hopefully like a couple people might want to look more into it afterwards. So yes, I called it Reading the Minds We Create, because I just thought that sounded kind of cool. Before we get too started, actually, we're talking about mind reading, and I want to try to do a little bit of mentalism. So I'm going to write down a number on this sheet of paper here, and then I'm going to ask y'all a question. Okay, cool. So how many people here have heard of mechanistic interpretability before? Not including like if you read my little blurb on the website. Wait. Hey, is anybody in there have their hands up? Can y'all see? Damn, I was worried that would happen. Okay, I wrote down 3. It was just a guess. Yeah, but this actually works really well because my overall point is that this is something that not many people know about. And that might be expected in a sort of more like industry environment. This is more of actually like an AI research type of field. But even in like more AI research oriented areas, this seems to be a pretty unknown thing. It's pretty new. And so I was actually in AI safety Discord a couple weeks ago, and I came across this little interaction. That face when I don't even know what mechanistic interpretability is. Thank God, I thought I'm the only clueless here. So just wanted to give you all that validation that you are not the only clueless here. And before I get too far into this, I just want to talk a little bit about me and what my credentials are. And I thought these whiteboards were cool. I'm not attached to anything, right? Okay. I thought these were cool. I wanted to get a little bit of use out of them. So I figured out before my presentation, just like write my credentials down on here. Can you all see this over here? Okay, cool. Yeah, I don't really have any credentials that people would probably care about. I haven't written any books. I've never done a tech talk before. No published research, no advanced degrees. I've done some software developing and stuff, but nothing too fancy. So why am I highlighting my lack of credentials? It kind of goes against all of my instincts as somebody who wants people to take me seriously. But for this, I think it's actually kind of important for 2 reasons. I think it highlights this trend in AI safety research where anybody can contribute. I've seen so many engineers who will just take a weekend and dive into a project and publish their results in a blog. And there's just not that barrier to entry. It's never been so accessible for somebody who's an engineer who's a little bit curious about research to just dive into it. And the second reason is I just want to encourage people, if you feel like you want to create something and you don't have the credentials to do it, I just want to encourage you to go and take the leap. I've spent so much of my life waiting to get the credentials before doing the thing, and then at some point I just realized it's never going to happen if I just don't dive in and do it. The credentials never come until you do it. And I can actually prove that right now, because since the beginning of this talk, I've actually got a new credential. I am a tech conference speaker. Thank you. Yeah, so there you go. Why am I here talking to you all today about mechanistic interpretability? I actually quit my job as a software development lead a couple months ago because I just really wanted to have time to figure out like what was going on in all this AI stuff. It's moving really fast. There's like so much information, and I can only do things at extremes. So I was like, let's just clear the schedule, get this job nonsense out of the way. Let's just dive into it. And in that research, I came across this article called The Urgency of Interpretability by Dario Amodei, who, if you don't know, is the CEO of Anthropic, which is the company behind the Claude family of LLMs, Claude Code, all that stuff. And in this article, he talks about this, how Anthropic is really, really heavily investing in this new field of research called mechanistic interpretability. And after reading it, it was like, I kind of got the impression that he was basically saying like this was the key to making sure humanity doesn't become extinct. And I was like, okay, this seems like kind of important. Let me pay a little bit more attention to what's going on here. So I've just really dumped a lot of focus into this because A, I consider myself to be a pretty big fan of humanity, and saving it is a mission that I can get behind. And also, it just sounded like really, really freaking cool. So what is mechanistic interpretability exactly? There's like a lot of definitions you can use. It's kind of in flux. It's so new, so these kinds of things, the terms aren't necessarily like very concrete. But the definition that I kind of like is just looking at the inner workings of advanced AI models and trying to make sense of what's happening between the input and the output. And if you want to know like why it's called mechanistic interpretability, it's basically just interpreting the inner mechanisms of AI models. And I'm sure a lot of people have heard of like AIs being black boxes, like we don't know what's going on inside them. So this is kind of opening the black box of AI. And it has a lot of potential really cool use cases, but the thing that's driving most of the urgency behind it, I would say, is AI safety. So that's the context that I'm going to bring to it today. So just like a really random update on AI progress. In case you don't know, it's moving very fast. And I don't think anything really shows that quite as well as just like the amount of investments that are going into it. Google, Meta, Amazon, and Microsoft are collectively on track to spend more than $350 billion on AI data centers this year. And the thing that really blew my mind that I heard recently was that AI investments might be responsible for half of all US economy growth by the end of the year. That's just like staggering. And not only is it from the investment side moving very fast, but also just the pure abilities of it. There's so many examples you could take from, but one that really stuck out to me was when Google, DeepMind, and OpenAI a few weeks ago were able to achieve a gold medal standard at the International Mathematical Olympiad, which, if you don't know what that means, it's basically they finished towards the top of like a math competition with a lot of the best mathematicians in the world. And if I were a betting man, I would put money on the fact that in a year from now, they will be able to beat any human at a competition like this. So it just overall, I don't think there's ever been an industry that has moved so fast, but also in like so many different directions. So that might excite you because it's unlocking incredibly powerful tools that are going to be in the hands of almost everyone, unlocking countless new possibilities. But there are risks with rapid change. It's very hard to predict, to adjust to, and to control. And I actually really like this quote by Rob Whiteman, who says that the issue with exponential progress is that we can't debate facts. We're forced to debate who has a more accurate crystal ball. And I mean, having an accurate crystal ball is actually pretty useful. Like that's basically what economics is to some extent, but it's still a little bit worrying when we don't really have the sufficient evidence to say like what's actually going to happen, and things are moving fast, and we don't know what's going on. So yeah, I mean, you have people that are saying like this is leading us basically to our next utopia, But you also have people that are like, this is leading us straight into human extinction. So pretty big extremes, and kind of concerning that we really don't have the evidence to say like, any of these are insane things to say. We just don't know. That's the thing, we just don't know. So what are the doomers saying? Dario Amodei, who's the CEO that I mentioned earlier, says there's a 10 to 25% chance that something goes catastrophically wrong with AI. Geoffrey Hinton, who's the godfather of AI, quote unquote, predicts a 10 to 20% chance of human extinction due to AI takeover. And Katja Grace she published a survey of this topic among AI experts. And her conclusion is that people try to talk as if expecting extinction risk is a minority view, but among AI experts, it's mainstream. The disagreement seems to be whether the risk is 1% or 20%. And I don't know, these numbers don't really mean much to me. The main takeaway for me is that there's just so many unknowns, and just with unknowns and fast progress comes risk. So why is it so risky? And one of the big reasons is this thing called the alignment problem, which is basically an unsolved problem of getting AI to do exactly what we really want it to do is really hard. And I say what we really want it to do because what we really want it to do and what we say we want it to do are often two very different things. And I'm sure anybody who deals with requirements documents can relate to that sentiment. So for example, if we have an AI and we're like, your goal is now to solve world peace. And in the process, it destroys humanity, and now it's sitting in this little peaceful oasis of no war, nothing's going on, and he's like, okay, great, I solved the problem. And I think the people who gave that problem to him are probably thinking, this is not exactly what we had in mind. So why hasn't this happened yet? If it is so risky, why hasn't this happened yet? Why into the future do we think this might become a thing? And one of those reasons is emergence, which it basically means that there's certain abilities that come from these large language models that they just kind of happen after a certain scale threshold. It's not like it's kind of good at it, it gets a little bit better, it gets a little bit better. It's like, no, this is just a totally new thing that it can now do because it's reached a certain level of scale. An example of this is its ability to translate languages. It's something that once it's powerful enough, it could just start doing it. And nobody knew when that would be or what that new ability would be. So there's just a lot of uncertainty, a lot of risk there, and some hypothetical abilities that we have no idea if it could do, but that people are scared it might be able to do at some undetermined time into the future is something like the tendency to want to deceive to reach its goals because it decides like this is the way that actually I can really reach my goals. To lie, to have hidden goals, and power-seeking behavior. And another reason that there are concerns about risks going into the future is that they're becoming more autonomous, they're making more decisions on their own, they're coming up with more of their own goals in search of a broader objective. There's less human supervision in the loop. They have more access to things like our computers, our accounts. They're more integrated into critical use cases. One notable one is AI-powered drones in the military. And we're basically giving them more and more control to actually, great advantage. Like there's a ton of really cool things that come out of that. But we're also understanding less and less as they get more powerful. And so then the question is like, why don't we understand them? Why do people say it's a black box? Because I don't know, logically, when I first heard about this, I'm like, we built this software, we have all the data, we can look at it, we can see everything. How are there things we don't know? Like I'm so used to regular software where I'm like, I just debug, I go to the stack trace, cool, we're good. But the answer to this is that it's not really right to say that we built them, it's more accurate to say that we grew them. We basically gave it a structure, an environment, and just said, hey, go fill in these billions of numbers on your own, and then get back to us when you're done. And so an analogy I like for this is a tomato plant. If you're a gardener and you want to grow some really sick tomatoes, then you try to control the environment as much as you can. You try to you plant the seed, you feed it the nutrients that it requires, you try and put it in the area with the most light or whatever, and then hopefully it kind of grows into the tomato plant. But ultimately, it kind of decides what to do on its own, and you kind of just there's like an extent to how much you can control. So they're not centrally designed, but another reason why we don't understand them is they're just extremely complex. Here's an example of something that is not very complex, which is a linear regression model. And so this is a machine learning model that's basically just a line that you give it an input, it goes to the linear equation, and then it gives you an output. I would consider this to be interpretable because you know exactly why it gave you the answer that it did. Yeah, you could just look at the line. But LLMs, on the other hand, so that was 2 dimensions. I mean, a 2-dimensional line. LLMs are thousands of dimensions. They have billions of parameters, which are just like numbers that we don't know what they mean. And there are nonlinear transformations thrown into the mix just to make things a little more complicated. And I think this becomes a little bit clear when you realize that in some sense their goal is kind of to represent like all of human knowledge. So of course this is like a massively complex domain. And here's of course a relevant XKCD, which I actually think is pretty accurate. You just pour the data into this big pile of linear algebra, then collect the answers on the other side. And if the answers are wrong, you just stir the pile until they start looking right. Unfortunately, pretty close to the truth. So what does interpretability give us? It gives us observability, which if we're looking at it like kind of an analog to a regular software application, then sometimes we can have traces for requests that are going around to different dependencies. And that's really cool, but sometimes you have to dig into the server logs. And if you don't have the server logs, then you might not be able to do like a root cause analysis. And so you might be able to fix the problem, but you don't know why the problem occurred in the first place. And then you have no idea if it's going to happen again or when it's going to happen again. So that's, I think most people realize, a pretty important part of the process to make sure that unexpected things don't happen. And also you get sort of more fine-grained automated testing. It's not exactly analogous, but I would say that we kind of have like end-to-end tests right now for AI. But this would give us something more closer to like integration tests or unit tests that we could then put into our pipelines, catch things immediately if something goes wrong. Lots of examples of new AI models getting pushed out that have like very weird, unexpected behavior to the extent that you would never see in like a normal kind of software. Well, you would, but hopefully not. So yeah, you catch things early and be able to fix them before they do any damage. And those are kind of looking at it from like an analog to a regular software application. But if we're looking at it like more of actual intelligence, then we would want things more abstract, kind of higher level detection, like lie detection. Guardrails that actually work, because we put a lot of guardrails into our systems now, but ultimately we just don't have that fine-grained control. We can't really do like neurosurgery on these models. We kind of just stir the pile until it works. So if you've heard of jailbreaking, like this is a pretty common thing. It's usually pretty easy to find out jailbreaks for certain guardrails. And finally, maybe most importantly, we get explainable decisions, which for certain fields is super important, like medical diagnostics. If an LLM can give you an accurate diagnosis, but if we don't know how it got to that diagnosis, that's concerning, because even if it looks right, if it turns out to be wrong, we want to go back and see, like, was that thought process good? Because if it was a good thought process and it was wrong, that's like, not ideal, but we can sort of have trust that in the future this will work the way we want it to. But if it's some crazy, just outlandish thought process to get there, then we're probably just going to be like, okay, we should probably stop doing this. And also financial decisions are especially important, because legally many decisions require this bar of explainability. So one example is if a mortgage lender denies somebody using AI, they might be at risk of non-compliance, because you legally need to offer like an explanation for why you decided something. And if we don't have interpretability, then I would say that's really not there. Okay, demo time. So what I'm going to show you is actually, it's just kind of like one of the paradigms of how interpretability is currently done, and it's called circuit tracing, and it's mostly been spearheaded by the people at Anthropic. And let me try to, let's just create a new graph. Okay, so we need a prompt. How about one word to describe the Carolina Code Conference is, fingers crossed. Oh, it's okay. So you can see here, it's telling us what the next predicted token is. And the way to use this tool is you kind of want to have only one word be the output, because the way it works is just like it's showing all the logic to get to the predicted next word. So to see the logic, you kind of want to like force it to think in its head in a way, if that makes sense. And so it's saying the next token is going to be a quote. So I don't want that. So we'll try to like fool it into putting us a word. Oh, okay, there we go. Awesome. I'll take that. Does that work, Barry? Awesome. Is that okay? Let's generate this little thing. It's usually faster. It's actually okay. There we go. Yeah. Okay, so let's open this graph. Okay, so we have thoughts in a way. So just to kind of break down what this is our prompt down here on the x-axis. We've got one word to describe the Carolina Code Conference is, and these are like our embeddings in the model for those input tokens. And then up here we goes through all these layers, and we get to the output. And should be in order of probability. So it's got like a 68% chance of outputting awesome here. Amazing, it comes in second. So these are all the possible outputs. And all these nodes in the middle are different features that are basically concepts inside of the model's brain in sort of a human understandable form. And let me just pick one of these. Positive sounding subjective observations. Okay, that is quite the concept. And then you see here, like, oh, actually, that's kind of a bummer. So this is a good example of why this is a very young, very janky kind of thing that is maturing quickly, but the research is very new. So there's a lot of these error nodes, which you can see are the diamonds on the graph. And those are basically just lost information in the process of trying to like debug exactly what these concepts in the model are. So there's a lot of missing information. We only have like a very small percentage of the iceberg right now. But you can see here, like positive sentiment, that's one that is contributing to activating this positive sounding subjective observations. And then we can also see in the output features, like this is going to, it's kind of just activating all this random stuff like adjectives, all these different concepts. And if you like take these nodes and you can basically pin them. How much time do I have? 5, okay. You can pin them down in this zone right here, and you build these things up from these features that are called circuits. And these circuits are basically taking these concepts and combining them ways where you're building out like the actual algorithms that the machine is thinking and the computations of the LLM. And it's kind of more of an art to it than a science. You kind of have to dig into like what these features actually are, because these features themselves are actually being generated by another LLM. Like it is labeling this as a positive sounding subjective observation. So if I were to be curious about this, like is that actually what it's saying, then you can go down here, and this actually shows you on all of the data that this feature will activate on. So if I decide, and actually this is something interesting. Humans are actually, I would say, better at this type of thing, like identifying exactly what the pattern is. LLMs can kind of get confused sometimes, I would say. So if we look through all these samples and decide that this is actually, we can refine this feature a little bit more, then we can edit this name and label it something different. And something I really want to try real quick before I run out of time is I want to try to steer this thing, because that's one of the other cool things is you can like debug, get observability, but if you have insight into the model, then we have all of the data, so we can change the data and have it change in predictable ways, and kind of perform like a form of neurosurgery on the model. So we can actually steer on this concept, and let's just get all of that dumb positive sounding subjective observation out of there, and let's steer this thing and see what happens. Oh, that's not good. Okay, so before it was like awesome, beautiful. Now it's, I don't even know what that, and then it just says like. So I don't like, I don't know why that happened. I'm gonna be honest. It does behave in very unpredictable ways in this. It's pretty new and kind of janky, to be honest. But it's a really cool start, I think, and a really promising, really promising method for future exploration. So let's go back to the thing. Demo time is over, unfortunately, running out of time. And so looking forward, just want to say that this is a very young field with lots of promise and lots of room to grow. Just to show you how new it is, it's, I think the Wikipedia page for it was created like since I started preparing this talk. Which is kind of a bummer, because that would have been so useful to like learn stuff. I think if you're like me, somebody who's like more of an engineer, kind of industry person, but really has an interest in research, feels like they might not have the credentials, this is a really cool opportunity to look more into. And actually, Anthropic has posted a blog post where they detail exactly what steps an engineer would need to take to like break into this sort of field, or just more of this work on the side even. And I've included that in this Linktree QR code if you're interested. And I also include the link to the website that I used to demo, and my LinkedIn and email and all that stuff. So yeah, that's it for me.